to heat. So that is just what I meant by that statement. That is, different body has what? Different what? Rates of expansion when subjected to heat. Let's look at the effect of expansion in our everyday life. In our everyday life, go to any coastal region or any place where you have ocean or river flowing, and a bridge is actually built over it. Now, each time you look at the length of your bridge, let's say this is a coastal region. Now, water is flowing normally. Now, this is point A and this is point B. You now decide to have a bridge, a crossover bridge. This is a bridge. Now, if the material by which they used to what? Construct this bridge is, let me say, they used a metallic beam. That is what we call metallic beam. Do you understand? If this metallic beam is not constantly being checked, do you understand? Either to reinforce it by replacing them. Either to reinforce them or to replace them. Every day by day, there is always what? Expansion. Do you understand? On the beam that what constituted this bridge. Do you understand? So immediately there is expansion. Immediately this bridge is experiencing expansion 247. You realize that the authenticity, when I say authenticity, the strength of this bridge is actually dropping. Do you understand? So due to expansion, a bridge can collapse. Why? Because heat from the sun is actually being sent on this bridge, and if it's not being maintained, it could collapse as time goes on. That is another very negative effect of what? Expansion. Another place where a negative effect of expansion could take place is what? A house. Homes are being built. You have a house built, let's say a 3-story building built. Now, what you need to know, if you go to a civil engineer now, civil engineers will tell you that this particular building, you need to do some cost estimate, you need to build it, blah blah blah. By the time you look at the rates, what they actually used to build it, definitely they will make use of beam. Definitely they will make use of some good concrete. You understand? Whatever that is being used to actually make the structure of this house to stand, if it is not constantly being checked, there will always be expansion. Do you understand? So that expansion too could make this building collapse if it's not always being taken care of. So that is that as regards the house. Another one is your railway. Your railway system. Under the railway system, there is what we call railway rings. They are like rings, you understand? They are always on the floor. Do you understand? They are like pathways. They are like pathways for every train to pass. Do you understand? When I say train, a train. A train is any particular motor or device that rolls. It rolls its rotor. It rolls its ring by which it used to move on this particular railway ring. Do you understand? So each time it moves on this ring, if you look at it, the distance in between these two rings must be constant all through for this railway to what? Have a smooth movement. But due to expansion, this railway ring can what? Move apart or it collapse. If it collapse, definitely at that point at which it collapse, whichever train that is coming, if you get to this particular junction, there might be an accident because the ring will just go off one of these what? The rotor which is rolling on this ring can go off one of those rings, and before you know it, fatal accident takes place. And at that junction, so that is why expansion plays a very important role in science when it comes to heat. So these are the little things or little effects of expansion in our everyday life. So that is all about that. Now let's go to what we call linear expansivity. That's another very good subtopic. Linear expansivity. Linear expansivity. Linear expansivity. Now, under our linear expansivity, we will be starting with solid. Linear expansivity or solid. Linear expansivity or solid. Before we go to linear expansivity, we will be looking at what is linear expansivity itself. Linear expansivity is defined as an increase in length per unit length for 1 degree rise in temperature. What do I mean? This is a cubic body. I'm taking my time to draw it so that you understand what we're actually talking about. This body has a length, it has a breadth, and it has a height. If the height was not supposed to be there, definitely it will be a plane and not a solid. A plane object is an object that has just 2 dimensions. While a solid object is an object that has 3 dimensions. Length, breadth, height, that's 3. A plane will have just 2 because this is breadth 2 and this is length. But because it has that height, that's what? A 3-dimensional object. So 3-dimensional object is what we are looking at. So we now say this particular body is being subjected by heat. What happens? It expands. You can see it has expanded to this internal structure of the body. Now it has now expanded to this new length. Now this new length, this is what? Increment in L. This is increment in, this is B. This is increment in another L. Now this B2 might have an increment. Let me put it this way. This B2 might have an increment. So this is increment in B. Let's say this 2. This is L2. Now, if the increment is towards this particular region, if the increment moves towards this way, we'll be considering B. If the increment moves towards this way, we'll be considering L. Do you understand? So if this particular body increases from this initial stage to what? That is the new length. It means that that body has expanded. So when they now say linear expansivity, for every 1 degree temperature, the initial temperature, let's say the initial temperature is θ1. For every additional change in temperature, let's say θ2, there is now an increment of what? L. That is changing what? L2. Do you understand? Immediately you experience that due to what? Small, sharp change in what? Temperature, leading to a sharp change in L, linear expansivity has taken place. That's what we mean when we say is a linear expansivity of a solid is defined as an increase in length per unit length for 1 degree what? Rise in temperature. Maybe you have a 1 degree rise in temperature, there will always be what? No matter how little it is, an increase in length. So what is the formula here? So another thing you must know is what? The SI unit. SI unit of what? Linear expansivity. Linear expansivity is denoted by alpha. And the SI unit is what? Per degree per Kelvin. That's the SI unit of linear expansivity. So our alpha is now giving us what? L2 minus L1 over L1 into bracket θ2 minus θ1. All is measured in per what? Kelvin. What is L2? L2 is your new length. That's the new length at which this particular body expanded to. L1 is the initial. That's the initial length. Now, θ2 is the new temperature. Do you understand? θ2 is the new temperature, while your θ1 is the initial temperature. Then the L is still the initial temperature. So if you computate all this, you'll be able to obtain the linear expansivity of that particular body when it expands. So that is all about linear expansivity. So let's go to another one, area expansivity. Area expansivity. Expansivity. Remember, for linear, we talked about length. For area, we're talking about area, as in your A. So area is represented with what? Beta. Beta to now be A2 minus A1, almost the same thing. All over your A1, all over theta over 2 over, minus θ1. Still measured in your per Kelvin. So linear is giving us what? Alpha, which is giving us L2 minus L1 over L1 to θ2 minus θ1. Now the third one is your what? Your volume. Your volume expansivity. Volume expansivity. So that one is giving us gamma. Gamma equals V2 minus V1 all over what? All over V1 into θ2 minus θ1. They are all known as formulas for calculating expansivities, whether it's linear, whether it's area, or what? Volume. Linear expansivity, area expansivity, and volume expansivity. So that has answered that. Now let's go straight to their relationship between your linear, that's your L, linear, area, and your what? Gamma. Alpha, beta, and gamma. What do we mean? Beta, which is your what? Your area specificity is always given as what? 2 alpha, which is equivalent to what? Alpha plus alpha, to give you your what? 2 alpha. While your what? Gamma is given as what? 3 alpha, which is given as related to alpha plus what? 2 alpha. Now because beta is 2 alpha, you can now say your gamma is what? Alpha plus what? 2 alpha, which is your what? Your beta. This is a very good relationship between gamma, alpha, and beta. So it means that in a particular equation, you can be given your volume, you can be given your length, and you can be given your area. If you are asked to calculate for everything, you can calculate your area expansivity, linear expansivity, your area expansivity. Just add them, you'll be able to get your what? Volume expansivity. So with that, let's proceed to anomalous expansion of water. Anomalous expansion of water. At this region, we need to look at, when you say anomalous, we are talking about the what? The funny behavior of water when they are actually undergoing expansion. What do I mean by expansion? When you put